In this video, I wanted to look at a applied problem, like a real situation where linear equations come into play, so we can kind of see the usefulness of these concepts. So let's just read the problem. It says the book value of an asset is what a company uses to create its balance sheet. Many assets depreciate in value over time. For example, some companies choose to model the book value of a vehicle using a linear function. Let f of x model the book value of a company escalate over time, where x is in years and f is in USD. So basically, x is going to be our independent variable, which is going to be the time, basically how long have we owned that Escalade for, and f will be the resulting value. So it's like f is its value at time x. And we're given a function, we're given the formula for that, negative 6,000x plus 60,000. And so what we're asked to do is interpret the slope and y-intercept and graph. How much will the Escalade be worth in 4 years, and what domain range makes sense for this function? So one of the points about looking at it is since it's a solved function, it's in slope-intercept form, and we can see, well, its slope would be negative 6,000, and its y-intercept would be 60,000. And if I could use that information to make a quick graph of what this looks like. And really, actually, when I forget if I made this distinction in an earlier video, but when I'm graphing something not very accurately, just sort of creating I usually refer to that as sketching rather than graphing. And when we actually graph on a grid, as we did with the absolute value function example from a few videos ago, that's what we call graphing. Basically, when you're being more accurate and graphing is a lot of points, that's what we call graphing. And we're just sort of sketching some of the basic elements of the graph. We call that a sketch. So sometimes I might distinguish between that. Anyways, it's not that big of a deal. But the y-intercept is 60,000. So that's what tells me, well, how much is it worth at the start? And notice that when I created this grid, actually I just used the positive x-axis because a lot of graphs of real problems don't use negative numbers. And like in this case, negatives don't really make sense because the number of years that have passed is x. Since we've purchased the Escalade, it doesn't make sense to be negative. And also the value of the Escalade doesn't really make sense to be negative either, though technically if you have a car that doesn't work and looks horrible, maybe it's worth negative money and you'd like to pay someone to get rid of it. But if you see what I mean, usually negatives don't, or a lot of times negatives do not make sense in real problems. But basically the y-intercept is 60,000, so that's going to be its initial value or the top, and its slope is negative 6,000, meaning over time it's going to decay. And basically every year it's going to lose $6,000 in value. So after 1 year, it's going to be down to 54,000. And so on and so forth. It's going to keep decaying at a constant rate over time. Because again, we can see it's linear. And you know the saying with cars, it loses half its value as soon as you drive it off the lot. Now, linear, this is just a model. This doesn't necessarily accurately reflect its value because we're not taking into any other variables such as how much has been driven and other things. But when you're doing simple book values of things that are being used, a lot of times you have to use some estimation. So that's kind of what it's saying. We're just going to use a line to estimate its value. So we don't necessarily have to do exact calculations. And then it asks, well, how much will it be worth after 4 years? Well, I could just continuously subtract 6,000 every year to figure it out, or obviously I could just plug in 4, because if I want to find f is the value and x is the amount of years, so f of 4 should give me the value of the Escalade after 4 years, which would be negative 6,000 times 4 plus 60,000, which would be negative 24,000 plus 60,000, which should be $36,000. And that would give me another data point on my function, which my graph is not exactly perfect, but again, that's what the difference between a graph and a sketch is. A sketch is something that can help us think about the problem at hand whereas a graph is designed to be more exact. And of course, you could also just type this function into your calculator and look at it that way. Okay, so then it asks what domain and range makes sense for this function. And this is kind of where what I was saying, where negatives don't exactly make sense. Like the domain is going to be x, the variable x in this example, which is the years that have passed. And in this case, it makes sense to start at 0 for the domain because, again, negative time usually doesn't make sense. Again, it depends on the situation. And notice that the domain, it doesn't actually make sense to go to infinity because at some point this line is going to have an x-intercept. It's going to cross the x-axis and go down to the negative side. And so the question is, well, where does that occur and when does it hit its value of 0? And since it started at 60,000 and was losing 6,000 per year, we could conclude that it would take 10 years, right? Because 10 times 6,000 would be 60,000 to hit 0. And so it wouldn't really make sense to go beyond 10 years because if it goes beyond 10 years, it's going to go onto the negative side of the range. And we don't want the range to be negative. And in the same way, the range would be, well, again, it's bottom to top of our graph. We know the top of the range is 60,000 because that was the maximum value of the car when it was first purchased. And then since it's going to be a straight line depreciation, it's going to depreciate all the way down to 0 by assumption, which just means that after 10 years, this car is basically worthless to the company, which again might not be exactly perfect, but you can see lines might not be perfect for all applications, but they're simple, and that's kind of one of the greatest uses of them in most cases.